Hey everyone, and welcome back to the channel. Today we re-diving into one of the most iconic charts in all of science, the periodic table. You've probably seen it hanging in every chemistry classroom, but what does it all mean? How did we go from just a few known elements to this beautifully organized grid of 118? Well, stick around, because we're about to unlock the secrets of the periodic table, and I promise, it's way more interesting than you might think. So let's start at the beginning. The periodic table is essentially a giant cheat sheet for chemists. It arranges all the known chemical elements in a specific order, and this order isn't random at all. It's based on their atomic number, which is the number of protons in an atom's nucleus. We start with hydrogen, number 1, over on the top left, and as we move across and down the table, the atomic number increases one by one. But it's not just a long list. The genius of the table is in its structure, the rows and columns. The horizontal rows are called periods. As you move across a period, from left to right, you're adding one proton and one electron to each element. There are 7 periods in total, and each one represents a new principal energy level for the electrons. Think of it like floors in a building. As you go down a period, you're adding a new floor where electrons can hang out. Now let's talk about the vertical columns. These are called groups or sometimes families. And this is where the magic really happens. Elements in the same group have similar chemical properties. Why? Because they have the same number of valence electrons. Those are the electrons in the outermost shell of an atom. Valence electrons are the rock stars of the chemical world. They're the ones involved in forming bonds with other atoms. Take a look at group 1, for example, on the far left. These are the alkali metals except for hydrogen. They all have just one valence electron, which they're very eager to give away. This makes them super reactive. Think of sodium and potassium. Drop them in water, and you get a very energetic reaction. Now jump all the way over to group 18 on the far right. These are the noble gases, like helium and neon. Their outermost electron shell is completely full, making them stable and very unreactive. They're the cool, aloof introverts of the periodic table. They don't like to mingle. So, you have the highly reactive alkali metals on one side, the stable noble gases on the other, and everything else in between. In group 17, right next to the noble gases, you have the halogens, like fluorine and chlorine. They are just one electron short of a full outer shell, which makes them extremely eager to grab an electron from another atom. This makes them highly reactive as well, but in a totally different way from the alkali metals. It's this beautiful pattern of reactivity that the table reveals. But who came up with this brilliant system? The credit mostly goes to a Russian chemist named Dmitry Mendeleev in 1869. Now, he wasn't the first person to try and organize the elements, but his approach was revolutionary. At the time, they didn't know about protons or atomic numbers. Mendeleev arranged the elements based on their atomic mass and their chemical properties. Here's the truly genius part. Mendeleev noticed that the properties of elements repeated in a periodic or regular pattern. But his table had some gaps. Instead of seeing this as a flaw, he boldly predicted that these gaps were for elements that hadn't been discovered yet. He even went so far as to predict the properties of these missing elements, like their atomic mass, density, and how they would react. He called one Eka aluminum. A few years later, an element named gallium was discovered, and its properties matched Mendeleev's predictions almost perfectly. The same thing happened with scandium and germanium. It was an incredible confirmation of his theory, and cemented the periodic table's place as a cornerstone of chemistry. Of course, the table has evolved since Mendeleev's time. His original table was arranged by atomic mass, but we now use atomic number, thanks to the work of Henry Moseley in the early 20th century. This cleared up a few inconsistencies in Mendeleev's version. And of course, we've filled in all the gaps and even created new man-made elements that extend the table further. So the periodic table isn't just a poster. It's a map of the universe's building blocks. It's divided into sections. You have the metals on the left and in the center, which are typically shiny, good conductors of heat and electricity, and solid at room temperature, with mercury being a famous exception. On the upper right, you have the nonmetals, which are generally poor conductors and can be solids, liquids, or gases. and snaking between them is a staircase of elements called metalloids, which have properties of both metals and non-metals. They're the semiconductors that make our computers and smartphones possible. Let's look at a few other key areas. Those two separate rows at the bottom? They're called the lanthanides and actinides. They're actually part of periods 6 and 7, but they're pulled out to keep the main table from being awkwardly wide. The actinides are particularly interesting because many of them are radioactive, including elements you've heard of like uranium and plutonium. The periodic table also helps us predict trends. For instance, as you go down a group, the atoms get bigger. As you go across a period from left to right, they actually get smaller, because the increasing number of protons pulls the electrons in more tightly. We can also predict things like electronegativity, an atom's ability to attract electrons, and ionization energy, the energy needed to remove an electron. These trends are not random. They are a direct result of the table's logical structure. It's a powerful predictive tool. If a chemist wants to create a new material with specific properties, they can look at the periodic table to find elements that might work. Need something that conducts electricity well but isn't too heavy? Look at the metals. Need an inert gas for welding to protect the metal from reacting with the air? Head over to the noble gases and grab some argon. Everything is laid out for you. From the hydrogen that fuels the stars to the oxygen we breathe, the carbon that forms the basis of all life, and the silicon that powers our digital world, every single element has its place and its story. The periodic table isn't just a list of ingredients. It's the recipe book for the entire universe, showing us how those ingredients relate to one another. So the next time you see a periodic table, don't just see a jumble of letters and numbers. See a story of discovery, a map of matter, and one of the most elegant and powerful tools ever created by science. It's a testament to our quest to understand the world at its most fundamental level. I hope this brief guide helped you appreciate the beauty and brilliance of the periodic table a little more. It truly is a masterpiece of scientific organization. If you found this video helpful or interesting, please give it a thumbs up. It really helps the channel. And if you want to explore more amazing topics in science, make sure you hit that subscribe button and ring the notification bell so you do not miss our next video. Thanks for watching, and I'll see you in the next one.